Okay, so today I'm going to talk about this integration problem as a deep dive and to kind of go over a few important concepts when integrating functions with trigonometric terms and like what are the general rules we can use for integration. So first thing we want to look at is see if we can use the chain rule. So if you look at the denominator, 1 plus x sine x, so if you differentiate that, so the x, the denominator, it's just gonna get cosine x, which doesn't really match with the numerator. If it does, then that would make this a perfect problem to apply the chain rule directly. So the chain rule is not going to work. Another thing is we can try integration by parts. So I mean, you're going to think about sine x dv equal to 1 over sine x dx. Well, if you just look at the right side, the dv is not going to go anywhere because we don't really know how to integrate the dv. So that's not going to work. So this didn't work, this didn't work. So maybe try another way of doing integration by parts. So if we take the denominator instead, so du is going to be minus cosine x 1 plus sine x square, right? Basically you just apply the chain rule and the negative comes from basically the reciprocal, the minus 1 power. So and then for v it will be minus cosine x, just minus cosine x. So then this is going to equal to uv, which is minus cosine x over 1 plus sine x minus, so there's a minus, so it cancels out, and cosine x 1 plus sine x squared dx. So it seems to look a little better, but not really, because now that, I mean, the denominator kind of got worse. Now it's square, and the numerator is cosine x, which, I mean, cosine square x, which if you try to differentiate the denominator, we need a cosine x here. So cosine square x, that's actually too much too. I mean, we can actually keep on and maybe try to do a integration by part for this interval, and yeah, actually I don't think it's gonna go anywhere. We can try, but I don't think it's a good idea. So I'm not gonna do it, because I mean this is gonna expand and gets messy. So I'm just gonna stop here and kind of declare that integration by part is not gonna work in this example. So what you really want to do is, when you see this kind of denominator 1 plus sine x, you want to apply the trig identity. I mean, we all know that sine x squared plus cosine x squared equal to 1. So then actually cosine square x equal to 1 minus sine square x. So this can be written as 1 minus cosine x, 1 minus sine x, and 1 plus sine x. So what we want to do with this interval is we want to multiply the top and bottom by the same 1 minus sine x. So for the numerator, we just redistribute. For the denominator, so this is 1 plus sine x minus times 1 minus sine x, and which basically it's this guy. So that's actually just equal to cosine square x. So this denominator with just one term is much easier to work with. Minus sine alright, so we make some progress, and at this point you actually, there's a few ways to tackle this problem. So I mean, the best way is to just recognize the secants and tangents in this form. So basically you have a sine and a cosine. Sine x, cosine x, and then there's a 1 over cosine x. That's the first term. Second term, you have a it's actually just tangent square, right? And the first term, it's actually tangent x times secant x. You should all know this one because that's just the tangent x secant x is just the derivative of secant, right? So basically, if you guys don't remember, which you should, so therefore this is just secant x. What about tangent square x? So there are a few ways to do this. One way is to just remember this formula. Tangent x is equal to 1 minus actually I don't remember what tangent x is equal to. I mean tangent square. So how does tangent square x related to secant square x? See, since I don't remember, I'm just gonna derive it here quickly, right? So it can be write this as 1 minus cosine square x, cosine square x, 1 over cosine square x minus 1. Okay, so it's secant square x minus 1. So this is tangent square is equal to secant square minus 1. Therefore, you can rewrite this as secant square x minus 1 dx. Square x. Actually, we should have written the plus c here. And then, what's the interval of secant square? Well, it's something that you should remember again, that the dx of tangent x is equal to secant square x, right? So therefore, this guy is just tangent x, and then this one is just x, right? So plus c. Well, this c is different from this c, but that doesn't really matter here. So there you go. That's the answer. Okay, so I want to show a few other ways that you guys can handle this problem. So one thing I want to note is that that is when people get to basically when they get to this point with these sine x, cosine square x, and then this sine square x over cosine square x, they might not necessarily recognize these forms. So I mean, what can you do? Well, actually, the truth is there's not a whole lot you can do, but by playing around with things, you might be able to figure out something. So let's look at A and B separately. So let's look at A. We are trying to integrate sine x cosine square x dx, right? That's A. So this one is actually pretty simple, because if you look at the denominator cosine x, so this is actually, it's just a chain rule. Cosine square x minus sine x minus, because if you take the derivative of the denominator square cosine, you're gonna get sine. So therefore the sine is, the minus sine x is just gonna get absorbed as part of the chain rule. Right. So then this is actually sorry, and then when you apply the chain rule, there's also a -1, because the cosine is in the denominator. It was a -2 power, now it becomes -1, so you divide it by -1. So this is actually just secant x plus c. And now let's look at B, which is sine square x cosine square x. So for B, sine square x cosine square x. So this is kind of the bonus, I guess. So how would you tackle this problem if you just don't remember those secant and tangent kind of integration? I mean, all you know is about derivative of sines and cosine, and you just don't know anything about tangent and secant. So we can try to play around a little bit. So I guess first thing, so sine is going to be equal to 1 minus cosine square dx, right? So then this, we can break it down into this. So now we have kind of figured out the x portion of it, but what about this left hand side? So this is actually pretty obvious that this is a cosecant square, and secant square, and that's somehow, I mean, we don't remember that. But now that we don't remember it, so we have to, I guess, find a way to really figure this out. So let's see. So maybe, actually, let me rewrite this. So we have figured out the x term, we have figured out the secant square term, now we just need this. So you can play with the trigonometries again. So what does that gets us? It'll be something like sine square x cosine square x plus cosine square x cosine square x dx. Doesn't look very obvious, so maybe I can rewrite it like this. So this is still the first term, and then for the second term I'm going to write cosine x. Okay. So what did I do? Basically, this is just cosine square over cosine square, which is just 1, and actually it's nothing different from cosine x over cosine x. So why do I write it in this form? The reason is this is the product rule of the derivative. So let's examine it. So what is the derivative of f times g? If you take the derivative of f times g, which is going to give you f prime times g, f times g prime. So can we recognize the f and g here? So we have sine of x, which, well, plus. Actually I'm gonna rewrite it the other way. So f times g prime, f prime times g. So if sine of x is our f, then f prime will be the cosine of x. So then, which means this we are calling f, this is f prime. What about the cosine x? If we call cosine x g, and we try to differentiate cosine x, what are you gonna get? You're gonna add 1 to the power, so it's 1 over cosine x. So basically, derivative 1 over cosine x is going to be cosine square x, and then you take the derivative of cosine, which is minus sine, but then since your cosine is in the denominator, that's going to give you another minus sign. So actually it's just sine cosine square x, and this is actually same as g prime. So you can actually write this as f times g prime by applying this formula. So it's basically sine x times 1 over cosine x. Well, which gives you x sine of x divided by cosine of x, and that will be the tangent x. So let's scroll back up. So we actually collected all 3 terms here. Basically, what is a? A is just secant square, secant x, as we have found. That's just secant x. And what is this sine square over cosine square would be? It's actually going to be, well, this thing is our tangent x minus x. Therefore, this is the tangent x minus x. Of course, inside is minus, so we put a parentheses around. So this is going to get us the same thing as we have gotten using the integration from tangent and secant. Okay, so if you look at this stuff, it's actually not very intuitive. I mean, not intuitive at all. And why does it seem to look much easier in this way? Actually, when we try to go from tangent square to secant square, and then from secant square we went to tangent, is because what we were actually doing in part B below is we're kind of trying to prove that secant square antiderivatives integral is equal to tangent x, and it actually does involve this product rule of differentiation, which is quite bizarre. And but yeah, so that's the benefit. We should, I mean, derivative of tangent equal to secant square, it's something good to memorize. I guess that's my point. Alright, cool. I guess I kind of went through a lot and go around this problem, and yeah, I guess hope you guys enjoy this video.